Welcome everyone. I'm Ksenia Sternina, Chief Business Officer at SODA and the moderator of this webinar series. Today we continue our Practical SDV Webinar Series with the third episode focusing on SODA.Sim and how you can get started with the vehicle simulation in just minutes. In our last session, we explored SODA Validate and its role in AI-powered software validation. Now we are shifting to fast and efficient simulation, helping you accelerate testing, optimize development, and ensure high-quality validation. And I'm excited to introduce Christoforos Chatzikomis, product lead for SODA.Sim, who will walk us through a quick start guide to launch and run vehicle simulation effortlessly. Let's get started. Chris, first of all, tell us a little bit about your background.
Thank you, Ksenia. Thank you. I'm product lead for SODA.Sim and have a PhD in vehicle dynamics, and I have 20 years of experience, first in academic research and then in the automotive industry, developing systems like torque vectoring, also working on motion control for autonomous racing. During those years and through my work, I have experienced, let's say, the challenge and value of utilizing appropriate simulation tools to develop and validate advanced control solutions. And today we will show, I hope we will show exactly that, how we can use these tools to accelerate your development and validation.
Great, let's get started.
So we'll start with describing exactly. Let me share my screen. So I will start by saying a few words for product. This is SODA.Sim. It's a simulation solution designed from the ground up for everyone, basically, from individual researchers to and universities to large engineering teams at OEMs. So the platform provides, as you can see, photorealistic visuals, and also it can provide high precision physics and sensor simulation, while at the same time we try to maintain a user-friendly environment to configure your vehicle and your scenarios. SODA.Sim is built on a modular architecture that utilizes the Unreal Engine framework, and the vehicle and the environment are simulated as atomic components, as plugins. So we have sensors, vehicle systems, virtual ECUs that can be implemented and integrated into the framework. And it can use a variety of tools and programming languages to integrate and develop those atomic components, such as Simulink, ROS2, C++, or Python. Just to give a few examples. Additionally, and we'll show that towards the end of our webinar, SODA.Sim provides seamless integration with our SODA-V tools, so we can have also perform advanced road scenarios as part of a hill test and test basically together with the physical ECUs in hardware in the loop mode. So let me start it by introducing our environment. So this is SODA.Sim, as I said, and this is our virtual proving ground environment. There are multiple levels that range from cities, motorsport tracks that we provide as a library, and you can select any of those levels. Today, we will perform our demo using our SODA Virtual Proving Ground that we have modeled based on our experience on physical proving grounds, on real proving grounds, where we have conducted a lot of vehicle testing. So the virtual proving ground includes a high-speed bowl for high-speed vehicle testing, testing the handling of the vehicle, a very long straight, a 1 mile straight that can be used for straight testing, and a very large skid pad area for any relevant testing. So today we're going to use our straight line basically to set up a vehicle avoidance test that can, to show you how quickly you can set up a test if you want, for example, to test the vehicle dynamics. So we go into editor mode, and also to mention, right now I have been navigating around the scene using the keyboard and the mouse, which is in editor mode, basically where we can add the components of our scenario that can be placed around using the arrows, but also we can use to be more precise. We can use, for example, the coordinates to set some numeric coordinates exactly as we want them. So we have added our vehicle, and the vehicle itself is a set of components, as I mentioned. So there are a lot of components that can be used, and each component can be activated or deactivated. So, for example, we can have our input for the vehicle can be based on the keyboard. So if I activate that and I start the scenario, I can simply drive the vehicle around by using the keyboard. But for this test, we want something more precise. So we're going to use what's called input AI, or advanced virtual driver that can follow the route. And we see also the mechanical components and electrical components of our vehicle. So we have a braking system, steering system, and we have 4 electric motors, which actually correspond to the layout of the real vehicle that we have based this model on. So it's based on the Charge67 that has 4 electric motors, 1 for each wheel. And we can see that each component can be parameterized. We can change, for example, the gear ratio for this motor that comes with an integrated single-speed gearbox. We can select the motor, the torque output on with which wheel it will be connected. So in this case, we have 4 motors, each one connected to one wheel. And we also have our vehicle dynamics model that is very precise and fully parameterizable. We can change all the parameters that we would like, so we can match the behavior of our target vehicle. So we can change things like the friction coefficient of each tire, also load, the tire parameter, for example, that we have for a magic formula tire model. We can change the geometric and the mass parameters of the vehicle and the weight distribution, change the characteristics of the suspension, the aerodynamics, and so on. So in this case, our model is pre-configured to match the model, the Charge67 model. So now the next thing that we need to do is set up the obstacle avoidance scenario. So for this, we can use, for example, some cones to add to the route. So the obstacle avoidance scenario is a very standard test in vehicle dynamics, basically where we test the stability of the vehicle in a maneuver that simulates basically a double lane change that to come to the original lane very quickly. So we will add some cones here, and we can very easily again place them, and we can select, for example, how many rows of cones we will have, and we generate, for example, 8 rows of cones. We can change things like increase the width of the lane and so on. So we set our first row of cones. We will add another one in the lane next to it. So we will again set the coordinates for them. So this will be basically our second gate through which the vehicle has to go through, and now we need also to add the third one. So it's very easy to place any component using, as you saw, you can set them precisely where you want them to be by using the coordinates. So now we have our three sets of cones. So we come back to our starting point, and we have to add a navigation route that goes through these cones. So from the scenario, we add a navigation route. In this case, we have the starting point. We just first do a straight line. Just have to align it a bit. To go through the middle of the first and the third gate. And then it's just a matter of adding 3 breakpoints that then we can use to get our navigation route through the second and perform basically our obstacle avoidance. So this is our route. We can also, if we want to be more precise, we can also import the route from coordinates like this. So we can use a CSV to import the coordinate. We can select if it will show up or hide during the scenario. And then we can also save now that we have finished, let's say, with the first part of setting up our scenario. We can create a new slot. So for example, we can save what we did so far. We can select a label and we can save this scenario so far. And now if we press run, basically our vehicle will run through the navigation route that we just created, and will go through the routes. Actually knocked some, driving through it, we don't hit any cones. So we can just move it a bit to the right, and we can also move our vehicle at the same position, and then we can save again our scenario. And we try again, and we, just to make sure that just without pushing the vehicle, we don't knock any cones down, the cones without any problems. Basically tries to follow the route by keeping up to a maximum lateral acceleration, so it's not really pushing the vehicle to the limit. So we can fix that by going to our advanced virtual driver, and what we will do actually is we will change the maximum lateral acceleration that it tries to achieve. So we'll set a very high number just to make sure that this doesn't limit basically the vehicle speed, and we will limit the speed just to a certain speed limit, to an entrance speed. Basically in this case we'll set 75 kilometers per hour. So approximately that speed, 65 to 75 kilometers per hour, is the usual speed where obstacle avoidance maneuvers are performed. So we can save again our scenario, and we can run it. And in this case, we should see that the vehicle doesn't decelerate, but it should keep basically going at 75 kilometers per hour through the whole maneuver. Now, the next step, what we can do is we can go actually in our vehicle dynamics model and add some more information, let's say, to help us visualize and understand what's happening. So we can draw, for example, the forces that are generated by the tires, or we can render some additional information on the scene. So for example, I will select to show the traction torque, the longitudinal speed in kilometers per hour, and also the lateral acceleration, which are, let's say, the more relevant information that you would check in a scenario like this. So now we get the visualization for the tire forces, the vertical forces, the longitudinal forces, And we will see during the maneuver, for example, that we have these lateral forces and the lateral acceleration that goes, for example, up to 9 to 10 meters per second square, which is what we would expect from this type of vehicle. So we see now that by default, and at this speed, our vehicle completes the maneuver, but we can try also to see, okay, but what's the limit? If we increase, for example, the speed, let's say, to 80 kilometers per hour, will we still manage to complete the maneuver? And let's check that. My expectation is that it would fail to do it because I think we were already very close to the limit. So in this case, we can go back and we can see, yeah, this is because I didn't save, this is restored to the previous value. So now we can start, we can check, we can change something different. So for example, we can change the friction coefficient of the rear tires to simulate what would happen if we would have worn tires. So in this case, I'm expecting that there would be the vehicle would become more oversteering, for example, and that's what we see here. We see that the back end basically it almost spins out. So we see basically that what we just changed in the vehicle model change the behavior of the vehicle, and for example, we can do the same by changing the front tires. So by changing the friction coefficient of the front tires to a lower value, we should see a different behavior. The vehicle will fail the test, but in a different manner. We expect it to understeer at the exit and not oversteer. So we'll see now that probably that what will happen basically is the vehicle understeers and hits the cones at the exit. So you saw that we can very quickly change any parameter that we want, and we can repeat the test almost instantly without any issues. We can change basically any parameter of the driver and control the maximum lateral acceleration or deceleration or the vehicle speed. So we can set it up, for example, to go very fast and see what happens. So in this case, we expect that really probably it won't be able to make. So actually, it didn't have even enough time to finish the first part of the maneuver. So also here, what we can show at the vehicle, we now talked just about some components that we used for this vehicle dynamics test, but there are a lot of more components that we can use that are more, let's say, suitable for things like ADAS testing or autonomous driving. So we have virtual cameras, LiDARs, radars, and so on. And we can simulate also other systems. And we have dedicated also components that are imitators basically of specific hardware suppliers that we have simulated, and we have worked with components that we have worked in the past. So for the next step, we can show how we can use a similar scenario that we have already set up to do an integrated hardware in the loop testing using the SDR rig. So I will close this scenario, and now we'll launch a different test. So the software-defined rig and the scenarios in that case are fully controlled through our SODA-V tool and our SODA Validate tool that it was presented in the previous webinar. And here we can have an integrated example of how we can run the scenario from the sim, but the behavior of the vehicle, the control of the torques, would be done not by the simulator itself, but the physical ECU that I have behind me in the software-defined rig. So, and you can see also that we have some physical devices, in this case, the brake lights that are connected directly to the ECU and are driven by the ECU in the physical world. And at the same time, we have the brake lights. Sorry, setting stopped. I will repeat the test. We have the brake lights activating on in the simulator. Sorry, give me a moment to share my screen again. There it is. So we'll repeat the test that we just saw. So we run the test first with torque vectoring off. And in this case, the simulator provides all the inputs that are required by the ECU. So we have a virtual IMU, for example, that provides things like accelerations and yaw rate to the ECU. We have all the steering sensor, the vehicle speed, the wheel speeds that all provide the information needed and the necessary feedback for the ECU to work exactly as it works on the same car. And the software that we're now have under test here and we're running on the ECU is exactly the same software that runs on the real vehicle with torque vectoring and everything. So we run the test with torque vectoring off, and in the next case, we will run it with torque vectoring on. So all the launching of the test and the changing of the parameters and changing the scenario, all of this is managed by our SODA.V solution, the web-based tool. So everything can be managed from the web, and we can select the test that we will run and run multiple tests one after the other and compare basically the results that we get. So now we run both tests, and we showed basically how you can go from in a few minutes to set up the obstacle avoidance maneuver in SIM, and then you can also use that scenario to test your ECU in an advanced vehicle dynamic scenario with SODA.Sim and a software-defined rig. So this concludes for now what I want to show so far. So Xenia, maybe we can proceed to some questions.
Yeah, we have a question here. Is it also possible to simulate time-dependent changes in the friction coefficient of individual tires?
Yes, that's a very good point, and it's absolutely possible to do that. So we can, and this gives me an opportunity actually to say that our vehicle dynamics model that we have developed is Simulink based, and we have integrated. We can modify basically this model, and we can integrate very easily features like this and change and provide this functionality. And also what we can do and what is also provide not just time-based, but also location-based changes of the friction coefficient based on the friction characteristics of the surface that the vehicle is on.
Thank you. And we have another one. How ECUs are connected to the SIM? What interface?
So there are multiple ways to connect it. So in the use case that we have just shown with the software-defined rig, we use basically the CAN module that's part of SODA validate of the software-defined rig that connects to the ECU, and that's connected through a virtual CAN bus to the SIM. So the SIM has a lot of virtual buses like analog and digital inputs outputs. It has CAN, LIN, any kind of networking-based interface like ROS2, and all that are part of the same virtual bus and can be connected between them. And also the SIM provides support to connect directly physical CAN devices like PCAN or a vector CAN device or Quasar. So we can use a combination of physical and virtual devices to connect the SIM to both physical and virtual ECUs.
Wonderful, thank you. And I have a couple of questions sending privately. What is the price policy for SODA.Sim?
Yes, let me share the screen. Actually, it's on our website. You can check it yourself, but let's check it now. So in our website, soda.auto, you can find all the pricing information for all our products. So for SODA.Sim in particular, it's part also of SODA.V. So as part of that, as individual product, it's priced at a per user per month pricing model at £50 per month per user, or 500 for the whole year. But also it can be part of the whole SODA.V package, which together with Validate and Create, it comes to £100 or 1,000 per month, or £1,000 per year per user. But also to start with, our SODA.Sim solution is actually for research, for non-commercial use. It's actually free, so all the essential functionality that basically we have showed today, except for the part that we have the integration with our software-defined rig, which is part of SODA.V. The rest of the functionality that we show today is part of our open source and free solution. So again, through our website, you can go to our GitHub page where you can find the build version, and you can download it and start using it right away. And that's free for non-commercial use.
Thank you, Chris. And I have another one. Can any producer of the vehicle components add their component to the SODA.Sim to be available for everyone?
Yes, absolutely. So that will actually be the topic of our third webinar, where we will show how you can use the SODA.Sim development framework to develop plugins and components for SODA.Sim. Not use it as a final product, as a build version, but use it as but develop your own components and plugins for it. So it can be done in a multiple ways. So for example, you can develop your own component in Simulink or C++, and then integrate it into SODA.Sim, and that's what we will show in our third webinar.
Amazing, thank you. And we have another question. Is the SODA.Sim physical model precise enough for vehicle dynamic testing?
Yes, absolutely. So our vehicle dynamics model was developed for our physical, for the development of the software that we did for the real vehicle, and it has been validated against the real vehicle with tests that we have, with experimental tests that we have performed on the proving ground, like skid pads, obstacle avoidance tests that we just showed, acceleration, deceleration, and so on. So it has been validated and be tuned to match the real vehicle. And of course, for matching this behavior to another vehicle, you would need some experimental data or some data from another simulation, basically to correlate against, but the model can be absolutely tuned to match any vehicle.
Great, thank you so much. And the next question is, can the simulator replicate extreme weather conditions like fog, heavy rain, snow?
Yes, so that's a big advantage that we get from using the Unreal Engine framework. So the Unreal Engine framework, there are a lot of tools that are already developed that can simulate things like weather conditions. So we can simulate, yes, exactly, any kind of weather condition, and show how this, or time of day, for example, and show how this would affect the simulation. So for vehicle dynamics, for example, that would need also to interact with the surface. So not just the physical weather in a visual representation, but also the surface would have to change accordingly, the friction coefficient of the surface.
Thank you. And another one, can it simulate driver distraction and fatigue monitoring scenarios?
So our advanced virtual driver, potentially it could be modified. It can be developed to develop this functionality to simulate what a distracted driver or tired driver, how it would behave. So we can change, for example, the parameters of this driver to make it worse, basically. If we are talking about using it also as part of a test workflow where we have a human driver in the loop and we use the simulator as a driver in the loop product, that's also absolutely possible if we connect, for example, the human driver through a steering wheel, and then we have this driver in the loop test. So I'm not sure if this covers the question, but both cases are possible, yes.
Amazing. Thank you, Chris. Thank you so much. I don't see any other questions. At the same time, I would encourage everyone who's watching us, if you have any other questions, please add to the comments. In 2 weeks, we're going to have another webinar where we can cover the questions you may have. Chris, thank you so much.
Yep. Just to add something for our next webinar in the SODA.Sim series. So on our next webinar, we will focus on more advanced use cases using ADAS, simulating ADAS use cases. So in that case, we will show how you can add virtual sensors to the scene, like camera and LiDAR, and how you can interact with external ADAS software to test it, basically using our simulator.
Amazing. Thank you, everyone, for watching us, and see you in 2 weeks. Thank you, Chris.
Thank you, everyone. Thank you.